Welcome to the battle of antibiotics versus bacteria, a survival story. Today, we join Dr. Nesma in the classroom to explore a critical mission. We'll learn exactly how antibiotics fight off harmful bacteria, and crucially, how those bacteria fight back. Our learning objectives cover the mechanism of action, bacterial resistance, and the rational use of these powerful medicines. To understand this battle, we first need to shrink down and look inside the bacterial world. Imagine a single bacterium as a fortified medieval city. It has a tough outer cell wall for protection, an inner cell membrane, tiny factories called ribosomes that build essential proteins, and a central library of DNA containing all its genetic instructions. When we deploy antibiotics, they attack this city in different ways. First, let's look at the cell wall attack. Beta-lactam antibiotics, like penicillins and cephalosporins, act like soldiers with pickaxes, breaking down the brick wall of the bacterium by inhibiting peptidoglycan synthesis. As they say, no wall means no survival. Another strategy is the protein synthesis attack. Antibiotics like aminoglycosides, tetracyclines, and macrolides infiltrate the city and shut down the ribosome factories. By jamming the 30S and 50S machines, they halt the production of vital proteins, effectively stopping the bacterium from functioning. Then we have membrane destruction. Certain tough antibiotics, like daptomycin, punch large holes directly into the bacterial cell membrane. This causes a catastrophic loss of membrane integrity, allowing vital cellular contents to leak out, which rapidly leads to cell death. A fourth method is the DNA attack. Inside the bacterium's central library, antibiotics known as fluoroquinolones act like giant scissors. They cut the glowing strands of DNA, blocking nucleic acid synthesis and preventing the bacterium from replicating its genetic code. Finally, we have the metabolic pathway block. Imagine a busy assembly line producing essential nutrients, like the folate pathway. Sulfonamide antibiotics act like traffic cops, stepping in to block this metabolic assembly line. By inhibiting folate metabolism, they ensure the bacteria can no longer grow. But bacteria are ancient and incredibly adaptable survivors. Deep inside a dark war room, a surviving bacterial leader rallies its troops. Faced with the onslaught of antibiotics, the command is given: activate resistance strategies. The fight is far from over. Bacteria have developed 5 main resistance mechanisms. The first is drug inactivation. Bacteria can produce special enzymes, like beta-lactamases, that act like scissors. They literally snip the beta-lactam ring of the antibiotic, destroying the drug before it can do any harm. The second mechanism is target modification. The bacteria change the shape of their own internal structures, like mutating their ribosomes or DNA gyrase. When the antibiotic arrives, it's like trying to fit a key into a lock that has changed shape. The drug can no longer bind to its target. Third is reduced permeability. The bacterium simply closes its gates. By altering or shutting down the porin channels on their cell wall, bacteria can deny antibiotics entry into the city. The drugs are left stranded outside, completely ineffective. The fourth defense is the efflux pump. Some bacteria build mechanical pumps into their cell walls. As soon as an antibiotic enters the cell, the pump actively sucks it up and violently spits it back outside. This is a very common resistance strategy against tetracyclines. The fifth mechanism is metabolic bypass. If an antibiotic successfully blocks a crucial metabolic road, like the folate pathway, clever bacteria will simply build a detour. They create an alternate route to bypass the roadblock, allowing them to continue growing despite the drug's presence. But where does this resistance come from? It has genetic origins. Bacteria can share resistance blueprints with each other through chromosomal mutations, jumping genes called transposons, or by passing circular DNA called plasmids. This sharing, often through conjugation, can quickly lead to multi-drug resistance. Resistance also has non-genetic origins. Sometimes, bacteria hide behind thick abscess walls, enter a dormant resting state where drugs can't affect them, or form sticky protective shields called biofilms on foreign bodies like medical catheters. Patient non-compliance with prescriptions also plays a huge role. The clinical consequence of all this is selective pressure. When we use antibiotics, we kill off the weak, sensitive bacteria. But this leaves behind the strong, resistant ones. With no competition, these resistant superbugs survive, multiply, and take over. It's the survival of the resistant. To fight back against resistance, we need the hero strategy, rational use. This involves an antibiotic stewardship program, where a dedicated team of doctors and specialists collaborate to carefully plan and monitor every patient's antibiotic treatment. A key part of this strategy is the timeout. 48 hours after starting an antibiotic, a doctor reviews a crucial checklist. They ask, do we really need this antibiotic? Is the infection confirmed? Are we using the correct drug, dose, and route? Can we de-escalate or shorten the duration? Smart prescribing is also essential to optimize therapy. This means transitioning a patient from an intravenous drip to an oral pill as soon as it's safe, and carefully adjusting the dosage to ensure maximum effect with minimum harm. Finally, we must avoid mistakes. This means crossing out bad practices on the prescription pad. We must avoid duplicating therapies, prescribing the wrong drug, or using antibiotics for viral infections where they don't work. Avoiding misuse is our strongest weapon. In the end, it's a delicate balance between the life-saving power of antibiotics and the looming threat of resistant bacteria. As Dr. Nesma reminds us, we must use antibiotics wisely, or resistance wins. The future of medicine depends on our careful stewardship today.